Before introducing the next picture, which is from the side of the EUPEX pilot project, Matteo Turisini, we will have, but at the closing of our session today, there will be a panel related to issues, challenges, and opportunities around both chips and systems. Carlos might be able to share more experience there. So be sure that you attend that part as well. So introducing our next speaker, Matteo is leading the co-design activity under the EUPEX pilot system, which includes a set of scientific codes, quite challenging, and there have been performance studies on several of the available HPC platforms. And we will be getting his perspective on the topics of our session. Thank you for taking our invitation. Please go ahead.
One moment, please. I thought I had downloaded it.
There is there.
Okay.
Hello, everybody, in the meanwhile, and thank you for the presentation. I am pretty new to this kind of audience, and please be patient because I'm also new in the HPC world. I'm not a researcher in HPC. I've been for over a decade technologist in particle physics, and I resonate a lot when you guys describe the effort you are doing at the microelectronics level, because I used to work at single photoelectron detection, and the daily life was something and debugging the firmware or invent some new online real-time processing elements to not introduce any bottlenecks. But in physics, the constraints are pretty tough. And this level scale, yeah, I resonate with the semi-dynamic guy when he said at clock cycle level. But now I am in HPC. And today I'm gonna share with you the experience you're having in a EUPEX project. Thanks to Carlos that introduced this couple of projects that are sort of child from EPI. And EUPEX is the one dedicated to the general purpose processor. So today we will spend a few minutes in introducing the EUPEX project, its baseline plan, the deviations that happen in the execution, and then after giving you the current status and near future perspective, the second half of the talks will be dedicated to application. Those applications were selected for co-design in the initial phase of the project, let's say the first year, and now they are using for final demonstrators. So I'm gonna try to fill the gap in this between. I am not an expert, but yeah, let's say another way. This presentation is very informal, and I will not go into technical details, but if you are interested or colleagues and students are interested, we are releasing very nice webinars. You can access them through this link, and let's start. So top level, EUPEX is an integration project, which means put together the technologies that has been developed in past European projects, and also technologies that are currently under development. The consortium is pretty balanced between academic partners, data centers, small, medium enterprise, and large industrial partners, and is funded by EuroHPC and national communities. The duration is 5 years from 2022 to 2026, which means, guys, I cannot write it, but it's 1 year and a half and we're done. Okay, let's do some context. The idea is to have some European solution for exascale computing and probably also for future. And personally, I think we all agree that Europe can absolutely can develop its own solution for CPU. And I mean, you are EPI, so you know very well this statement. But ARM is around from many years for energy efficiency, but it implies also a microelectronic change in paradigm because of chiplets, because of specialized IPs, and also because of this fabless model to provide chips to the users. Europe has also done another thing, which is propose its own solution to go to exascale class machines, which is heterogeneity at system level. And this is something that we inherited from the deep projects. And we are in EUPEX, we really focus on this, as you will see. But in general, the world is becoming complex. The world is becoming also burning, but this is another story. And if you are used to think about applications as you did in the past, now applications are something much more complex. And I prefer to use the word workflows. What we are really in love with in EUPEX is to break down these workflows and try to find the best hardware accelerator or best machines to execute a portion of these workloads. And the modular supercomputing architecture is there for this reason. Another general thought we can do is that sometimes applications or workflows require some modernization. And this must be done without losing the validation experience that we have from decades of testing and production. So in general, as Carlos said before, we all want to increase the maturity of the ecosystem in Europe and also extend the community users. There are many attempts to enlarge the users of HPC systems by adopting cloud solutions. But also another trend is to increase the portability and maybe also reduce dependencies or increase the adoption of open source code. Personally, I also think that, it's also time that Europe starts thinking about itself, that Europe can lead some sort of transformation, but this is a really hard task in this world. Last general consideration is about society. Today, you will see a few 8 applications that we are taking care of inside EUPEX, but the idea is to feed back to society what they gave us in terms of money with this European project. And my idea is to new digital services are useful for human development, education, healthcare, and also agriculture. You will see one of the presentation there. So baseline plan. For objective, co-design in the beginning, deploy a platform, demonstrate, and take care of the applications. This is the first, to my knowledge, attempt to integrate the full spectrum of European technologies in one platform. So we have contribution from existing and past projects, from architecture aspects like the rack or the modular supercomputing architecture, to the processors, to the interconnect, system software developed, for example, in deep sea projects, and also profilers and tools that can help with some level of automation in make your code more efficient, not only in terms of speed, but also in terms of energy. And many open source initiatives are encouraged. For example, Scorpion and Scalaska are two examples of them. And applications are the key. So at the beginning, after the first year of the project, this was what we had in mind, a rack with general purpose module and another rack with with the GPU module. Of course, the sides of these two systems are different. So in one case, we are able to house almost 100 nodes per rack, and in another case, only 32. And we started very well. The co-design part was really useful. We took the application experts and sit around a table for many months with hardware developers, and we end up with this kind of design. In particular, the Work Package 3, the one dedicated to application, made an intense test campaign on the ARM features that the x86 does not have. And in the first 2 years of the 2 years and a half of the project, many reports have been produced. The one from WP3 are public, and the one dedicated to scalar vector extension and high bandwidth memory is really interesting if you want to get our experience in more detail. But simultaneously, we also worked on the hardware part by designing the motherboards, the blades, study how to integrate all these technologies, and also contribute to define the ecosystem, which means I have all this stuff. I want this, I don't want this. I can merge these two products. Last year, when I entered the project, the review went well. I cannot bet on what's going to happen in the next one, but when I was not in the project, the reviewer said all work packages delivered with high quality, but the project is at risk due to GPP delay. So what we did in the last year is to think about possible mitigation plans depending on the exact timing of the RIA CPU. And we end up with the worst scenario, which is the tape out in June 2025 or July. And this created materialized problems with us because the project is going to end in 2026, and we're going to have a second half for 2026 pretty dense. This simultaneously also creates some other impact, but this is what we have now. Probably the beta system 1, beta system 2 is something sounds a bit old, but yeah, I can describe it this way. When we got the RIA chip, we can finalize the blades and start the production. And then we need time to test and install it. So what you have in this slide here is that we will be able to test only in EVT version the general purpose module. And in this scenario, we will not have enough time to test application on this extensively, at least. This is a situation. Moreover, we had to drop the GPU module because of time mismatch with the RIA tape out, and so the collaboration decided to some way decouple the two things, hardware and software. Here you have the hardware in this sketch. And what happens to software is this one. We identified Grasshopper as the state-of-the-art platform for European applications. And so we start working with this kind of architecture. We are currently installing an SDV with 4 nodes at Evinen, and it's about 1 year that applications started working with this architecture. So we are really ready to have our last year of the project working with this SDV, trying to maximize the software result of this project. And this activity will be done in an interesting way. So far, applications owner were free to decide which kind of tool to use at any level. Runtime, job optimization, energy measurements, whatever. Now we are identifying together with ecosystem work package colleagues a certain number of demonstrator to demonstrate the level of maturity achieved by the project. So it will be a combination between European tools, European applications. And so far, at least we have identified 2 of them. One is related with this management of workflows, and a lot of other application teams express interest on energy efficiency. So this will be 2 directions for the next year. Applications. We are in the second part of the talk now. Sometimes it's good to modernize the codes, but things are also evolving because of the other specialization and whatever. I think on this part, programming models, other specialization, I think you can resonate, and probably you know better than me. Okay, just to introduce, we have 8 applications coming from something that is around Europe since years. The idea of digital twin of the Earth will help in understanding how our world is evolving and how to adjust our communities to adapt. So we have weather forecast application. We have a team dedicated to let's say increase the technology contribution in agriculture in terms of prediction of the crop. And also we have an interaction, powerful collaboration with satellite observation from the Earth. Another aspect is related with seismology and civil engineering. Another application is related with it's a sort of enabler for Industry 4.0. But since few years ago, when the project started, we had some problems with healthcare. There are also a couple of applications dedicated to biochemistry. And as let's say fundamental research, we also have a cosmological simulation code, which is called Gadget. And SKA is worldwide level experiments for astrophysics. Couple of mini apps about video coding and sun physics simulation will not reported today, but are part of the project. If you want more, probably EUPEX 2026 is one occasion. We are preparing a workshop there, and as I said before, webinars are out there on YouTube if you want to review them or review. Offline or new ones will come. Okay, to complete the general view, I created this Frankenstein application by adding all the characteristics of our applications. So in terms of language used, library, use or not used GPU offloading, file format libraries, general, let's say, deploy environment, resource management and file system, and some also storage requirement. In the central part of the right column, you have the full software ecosystem in EUPEX. The resolution does not allow you to appreciate all the things, but yeah, there are system management, user level, something that can be done from system administration, and everything you need from an application to the hardware, included runtimes. And in the bottom right, you have the picture of the Grace Hopper Superchip, which is going to be our final platform. If I have time, a quick overview on the application, just to give you some idea, some feeling about what our application experts are creating. For example, integrated forecast system is working. Okay, it's a production code for weather forecasting mid-range in Europe, and worked a lot both in vectorization and HBM studies, but recently many components of the ocean part, the physics of the ocean have been ported to GPU. And what they're going to do is to interact with our MSA team, especially for the IO part. One of the action, at least at the beginning, was that automatic vectorization was not enough, and they had to use intrinsics. Yeah, for this, I think it's enough. This is fostering precision agriculture. It's about predict crop results in a territory given the meteorological condition. They have to calibrate their agronomic model, and this is a CPU-only code. It is deployed using Docker, and they are able to create maps like this that shows that in 40 years is going to be the yield in Europe can be seriously damaged. So this is something that, I mean, all the community must be aware. It's something, it's a projection, but we will see. Yeah, if you grab an image from the satellite, probably you have something darkish that you see there on the left. But if you run some machine learning stuff, you can grab some insight from this image. For example, the amount of grass, the amount of water or snow. And the colleagues from Ulish, they are devoted to produce time series from these satellite observations, and they use machine learning methods. They have a very nice scalability intranode, but very poor scalability internode. So the interaction with other European projects devoted to networks will be very important. For the moment, they are ported the code, part of the code on NVIDIA GPUs, and they are doing really interesting stuff, which is adjust the work point of the GPU boards. This is something that, I mean, in a data center is not at user level. And typically we use the data center, the machine, as we are doing a limpak, which means wasting a lot of energy. And what they are observing is that just by reducing the clock speed at 95%, I mean, losing 5% of performance, you got 20% of energy savings. So you can produce the same science consuming less. Also, seismology is important. I'm a bit running out of time. This application is the collaboration between INGV, which is the Geophysical Institute from Italy, and Cineca. The interesting thing is that this will be our first demonstrator for which we will use Streamflow, which is a workflow manager from University of Turin, to make a first demonstration of this application here. Also, mechanical engineer it's important stuff. They work with the sparse and dense matrices. They had studied a lot the performance using A64FX CPU, and they expect to have higher performances because of the microarchitecture of the RIA cores. And again, at the moment, they are porting part of their application to Grace Hopper. And so, no, they completed, sorry. Biotechnology, yeah, this is very important. This is a problem of electronic interaction between a ligand and places in a protein, and this is used to reduce the budget in drug discovery. Now, from the idea to the pharmacy, it takes you €1 billion. If you can reduce a lot the testing part by simulating the interaction, you can speed up the process and save a lot of money. So also for Europe, which is a pretty old country, can be interesting. And again, they are at the moment performing energy consumption studies. Big DFT at the same level. The characteristic of them is that they are really focused on performance portability, and they made a lot of effort in using SQL as programming model. And they are actually testing on AMD. Gadget is the last one, is about astrophysics. They completed the porting on Grace Hopper, and they are intensively work on sparsity benchmark and how the scalar vector extension can help this part. Done. Summary. EUPEX is very ambitious project, and it was supposed to be the first platform integrating the full spectrum of view technologies. It's still like that, but not all the objects can be achieved in time. We dropped the GPU module. The GPP module is still possible in the time frame of the project, but this really depends on the availability of the RIA processor. Recently, the collaboration took a decision to valorize the software and indicated the Grace Hopper as the state-of-the-art platform. The goal now is to demonstrate the project results by creating a few demonstrators combining system software tools and applications, trying to reduce the dependencies, especially on proprietary software. And of course, we will continue the entire lifetime of the project to produce an industrialized server hosting the EPI general purpose processor. Thank you.
Questions from the audience, either in the room or from the remote attendees? Yes.
Thank you very much. Very, very interesting presentation. I'm wondering, so you highlighted that you cannot really test all your software on the RIA platform because it's not been there for some time, and that you're using Grace Hopper.
Yeah.
And yeah, you're trying to characterize the performance of your benchmarks on the Grace Hopper. Do you think that there is the possibility, I mean, to map the results that you're getting now on Grace Hopper to the RIA platform? Do you have model allowing you to some kind predict the results that you might be able to get using RIA?
I mean, based on the specifications of the two kind of cores, yes. The Grace CPU was chosen because it's intermediate in terms of microarchitecture between RIA 1 and RIA 2. So probably Grace could be slightly better than RIA 1, but I don't know. We don't have a model to project back the stuff. Many teams observed that still a lot of manual tuning is required. To continue support the general purpose processor, however, some of the application teams will continue using the let's say Cyper branch of the LLVM compiler. So at least to check that the compilation can be done, but without the platform.
Right. Further questions? If there is another question, can you comment about the A64FX possibility? I understand that this was investigated earlier in the project. If you have
Correct.
a comment,
Correct.
it is considered a pioneering machine, but I guess it is